This is the course in artificial neural networks, which has been given at Rhodes University in South Africa for many years now. Started back in the days of the 486 computer when a megabyte was a lot of memory. So training these things back in those days took many hours, and one had to be quite careful about the code. But I also thought that because there's such interesting and useful mathematics underlying neural networks, which you need if you really want to understand what's going on, it would be good to make a course for our honors students. So this course is not just about making artificial neural networks. It centers on a lot of the theory behind them. There are many good books on neural networks out there, but a lot of these are written by computer scientists, and they don't actually show the person how to make a neural network and deploy it for scientific purposes. So there are two objectives in this course: to look at the underlying mathematics and use it to make neural networks theoretically, and then to use MATLAB, the MATLAB toolboxes, to make and deploy neural networks to solve serious scientific and industrial problems. The underlying mathematics that you will need is the multivariate calculus, which is usually given in a second year course at a university. You will need linear algebra, which is also usually given in a second year course. And I'll go through the relevant mathematics which you need, but ideally you should have completed a course in multivariate calculus, especially the notion of the gradient vectors and linear algebra. And I'll go through some of that in this course. So this is what we will need for the theoretical background to make a neural network. And for the practical background, we need MATLAB. This is going to be the computational environment. I've got a set of notes on scientific computing with MATLAB, which I'll upload. But at this stage, I'm assuming that the person doing this course is MATLAB trained, so that you can write simple code in MATLAB. And then this is all going to combine to give you the ability to understand what is going on in a neural network and then actually make it and deploy it with MATLAB. Just in case you're interested in who I might be, this is a picture of me at Franschhoek. And if you go to ResearchGate, you can have a look at the publications that I've put out, and a lot of them in the realm of topology and uniform spaces and fuzzy uniform spaces and convergence. And then when finally someone wanted me to do something useful, I learned about neural networks, taught my students about it, and got alongside researchers at Rhodes University in the fields of biotechnology, biochemistry, chemistry, pharmacy, economics, and that the input that I managed to provide from that is produce many masters and PhD students in various disciplines. Neural networks are very applicable to all sorts of fields of investigation. As I said, we're going to be using MATLAB for the computational environment here. And if you go to mathworks.com, you can see the many toolboxes that they offer. And for this course, you will need MATLAB itself, of course, and then you'll need some of the toolboxes. So I'm assuming at this stage that you have acquired MATLAB and that you've set it up on your computer and that you have installed the deep learning toolbox. That is the primary toolbox that we need. The statistics and machine learning toolbox is also very useful. And I've got the symbolic math toolbox, which is very nice as well, but we don't need this for this course. So I'm assuming that you've got MATLAB, the deep learning toolbox, and this is desirable. And not, when you think of what you get with MATLAB, it is not that expensive. The deep learning toolbox you can see the contents of it, and deep learning has been shown to be extremely useful, especially for pattern recognition. But for this course, we're going to use mainly this section here. And if we can just expand that, then way deep down in this is define shallow neural network. So when I first started giving these courses on neural networks, they were just neural networks and there was a neural network toolbox. Now, deep learning has taken over because of its great applicability and usefulness. So what I used to do is now called a shallow neural network. But these can have amazing applications, very, very useful applications to all sorts of areas of research, useful for scientific research and useful for industrial applications. So this is the part of that toolbox which we will be using to make our neural networks. There's a lot more to this, which we'll talk about later. But first, we're going to look at the underlying mathematics behind neural networks. We're going to create problems which we will solve with neural networks. So we won't be using this for a while. We're going to establish some theory first, and then we will use this particular part of the toolbox to make neural networks. And you'll see there's a vast array of problems that can be solved with these. I produced a set of notes for the students in this course, and this is the first chapter, and this is what we'll be covering in the first few lectures here. And I'll put up the remaining chapters later. Many scientific investigations involve investigating some process, and from that process you make observations and record data. From the data you make some sort of model, a mathematical model, which is meant to model or approximate the process itself. You can use just equations perhaps, or systems of equations, differential equation or a system of differential equations, and so on. But whatever you have in your model, you need to then make sure that the model in fact does describe this process. So you need to then check your model against the actual process itself and see if the model is really simulating this process accurately. And one of the tools that we'll use is this notion of regression, which I'm sure most of you have come across before. So we're going to set up a model, and we want the output of the model to approximate the actual data in an optimal way, which I'll make clear. In the simple case where you've got one independent variable and one dependent variable, real numbers in, real numbers out, then we can represent the data on a graph. Say it looks something like that. So you've got data readings here. This is the x value, the independent variable, and the y value, the dependent variable. Input, output, input, output. And we'd like to know what is the relationship between the inputs and the outputs. Ideally, we'd like that as a function. This one, for example, looks something like a linear function. And we can then employ our own human intuition, our knowledge of functions to make an educated guess as to what function underlies that data. And then we can fit the graph of that function to the data and in an optimal way. And this is called regression. And the simplest kind of regression is linear regression, which I'm sure you've all seen. But let's just go through it because the ideas are important. So we've got a collection of data points, x1, y1 up to xn, yn. We've got n data points. The x's are the independent variable inputs and the y's are the dependent variable outputs. And this looks like a linear function here. By the way, I'm using linear, expression linear rather loosely. A linear function, strictly speaking, a linear function of x is one such there's a constant m so that y is equal to mx. That's linear. It preserves linear combinations. But let's just abuse notation a little bit and let this function, which is normally called an affine function, but we'll call this a linear function. It's of the form something x plus something, a1x plus a0. And now we're looking at this data and we think that, yes, a straight line can fit through those data points. So we're going to find which straight line fits in an optimal way through the data points. Now, what do I mean by optimal way? Well, we'll make that very clear now. What we want then is a function of the form a1x plus a0, so that the values of the function just fit in between these data points. Well, suppose here we have the n inputs, the x1 to xn, and these are the corresponding outputs, y1 to yn, and we represent this on a graph. So for each xi, the value of the fitting function is that linear function at xi, and there's its graph. And there's the corresponding yi, the data point. So there's xi, yi, the ith data point. And here is the ith value of that fitting function. And in general, there'll be some error between these two. And we'll call that ei. So e is a vector whose components are these errors. The vector e has components e1 to en, which is given by the differences between the fitting function and the actual data points. And what we need to do is minimize the norm of that vector, the length of that vector. And the length here is normally the square root of the sum of the squares of the components. And instead of trying to minimize the length, which has that square root, it's equivalent to just minimize the sum of the squares of the errors. Let's try a calculus approach to that problem. Remember, the problem was to minimize the sum of the squares of the errors. And we'll write that succinctly using the sigma notation. And I've got to set the two partial derivatives of s with respect to a1 and a0 equal to 0. Yes, s is a function of a1 and a0. x1 and y1 and all of the xi, yi's are just constants. The variables here are the a1 and the a0. So s is a function of a1 and a0. So we set the SDA1 equal to 0. Write down what the SDA1 is. It's the derivative of a sum, which is the sum of the derivatives. And we need the chain rule, so we differentiate the bracket to the 1 and then differentiate inside with respect to a1. So you get the xi. Do the same for the SDA0. And there we are. Now we differentiate inside with respect to a0 and get 1, which has been suppressed. And then if we gather those all together and clean it up, we get a system of two equations in two unknowns, a1 and a0. So let's look at it again and write it in matrix form. So it's a matrix applied to the unknown A1, A0 equal to a vector. And let's make that even more succinct. We write this as a matrix M, that's this one here, and the vector A, which contains the components A1, A0, equal to this B here. And we want to solve for A1, A0. We want to find out what A is. In order to generate what we can call toy problems, I've written a function called perturb, which takes a vector y and perturbs each of its components by a percentage e. So it's not very clever. You just take your y values and add a certain amount to them, obtained from this random number generator. The usage can be shown here. So we get y is actually 2x plus 3, but we don't want the y values to be exactly that. We want them to be perturbed around that. So we perturb by 10%, and then we plot the new y's. So there is the old y, and the new y is the old y perturbed by 10%. So it doesn't just give us a straight line. These are all values around that. And let's just see then how we can use what we discovered previously to fit a function to that data. Right, so that's the equation that we're trying to solve. So we can compute these 6 values, these 4 in this matrix and these 2 in this vector on the right-hand side. So we just compute those and form the matrix M. So M is that matrix there. And now we've got to solve. And there are many ways of solving. If this matrix has an inverse, then we can just take the inverse of A, of this matrix M, and multiply by B to get A. We can use Gauss reduction, and MATLAB has the backslash operator. If we try to solve M A equals B, then A is equal to M backslash B. That's a MATLAB function which is available. And that produces the vector A, which contains the coefficients. So the A1 is the first coefficient, and A0 is the second coefficient. And then we make a function and then plot it. And that's what it looks like. So that is a way then. That's linear regression. This is what you learned a long time ago. And it enables you to fit a linear function to data points. So there's our function which fits the data points in an optimal way. Right, now this is very simple, and most processes you come across in the real world are not going to be linear. Sometimes you can approximate them by linear processes, but in general they're going to be non-linear. So although this is very useful in very simple cases, it's not going to apply to a whole lot of things in the real world. There's another way of looking at this, and this gives us an introduction to what is known as a pseudo-inverse of a matrix. So here we are again. There's the A that we're looking for. There's the error vector. You can write then E to be this matrix here. Just think about it. You're taking A1 times all the x's plus A0 times all the ones. That's how matrix multiplication works. Again, get out your piece of paper and make sure that this just gives you that. The A1 x1 plus A0, A1 times x1 plus A0 times 1. That's that first one minus y1. Make sure that you are happy with that. That's the error vector. So it's a matrix which we can compute. We know the x's. Here's the unknown, and there's the y values which we know. So we'll write that as M, call this matrix M now. It's not the same as before. We'll call this one M. A we're looking for minus y. And now what do we want to do? We want the length of this error vector to be as small as possible. We want it to be a minimum. So we're trying to minimize the norm of MA minus y. Now, that M is an N by 2 matrix. N here, 2 here. Excuse me, that's my phone going off. All right, so this is what we are trying to minimize, this error vector. Let's just get some notation and terminology sorted out. If I've got an M by N matrix, I'm going to use this notation. The jth column is going to be denoted by A superscript J. So here's the picture for it. Here's the matrix A, and the jth column is denoted by A superscript J. And in MATLAB notation, it's A, and the semicolon there means all of the rows, jth column. All rows, jth column. Then let's define what we mean by the column space. The column space is all linear, the set of all linear combinations of these columns. So it's the set of all elements of the form x1 times a1 plus x2 times a2 plus x3 times a3. All linear combinations of the columns is called the column space. Also, it's called the span of that set of columns. And let's use this curly C to mean the column space of A. It's a vector space. It's the set of all vectors which can be obtained by linear combinations of the columns of the matrix A. So if we're looking for a solution X to AX equal to B, this is what we're looking for. It's a vector, a list, X1 to Xn, and that combination of these columns gets to be B. So x1, a1, a plus x2, a2, and so on. That combination of these columns actually equals B. And that means that B must be in the span of all of those columns. In other words, B is in the column space of A. So that's what it means to get an actual solution. If AX equal to B has a solution, then X is that linear combination of the columns of A which gives you B. So B is in the column space. And that means the rank of A, which is the dimension of the column space, doesn't change if you augment A by the column B, because B is a linear combination of the columns of A. In the case where this is a square matrix, if M equals N, then the determinant is not 0, and we can find the vector X by taking the inverse of A times B. If M is less than N, in other words, if there are fewer rows than columns, then there'll be infinitely many solutions. But in the other case, where we have more rows than columns, then B may not be in the column space of A. And what we're trying to do then is to find a vector X so that AX is as close as possible to B. So here, this line here is meant to be the column space of A. So I've shrunk it down to be one-dimensional. Of course, it'll be n-dimensional in general. But say this is the column space of A, just represented here artistically, a line. Then in this column space is all the combinations, all the linear combinations of the columns of A. And we're looking for this particular combination of the columns of A, which is then AX, which is as close as possible to B. In other words, such that this distance, the norm, the size of the vector B minus AX is a minimum. Now that is what we would want, and geometrically speaking, that means, just looking at this, that this vector b minus ax, this one pointing up here, is orthogonal to the column space of A. That's the notation we use for orthogonality. And if ax and b minus ax is orthogonal to all of the column, to the whole column space, it's orthogonal to all of the particular vectors in the column space. In other words, to all of those columns of the matrix A. So for every j, b minus ax is orthogonal to aj. And orthogonality means that the dot product between the two vectors is 0. So aj dot b minus ax is 0 for every j. And when you achieve the dot product of two vectors, if they look by default, vectors for us are column vectors. So aj is a column and this is a column. Well, then you take the transpose of this. Transpose of the vector times b minus ax, that forms the dot product. Make sure that you're comfortable with that. So column vector dot column vector is achieved by taking the transpose of j, which is now a row vector, times this column vector. And that means if we now multiply this in, the whole of A transpose times B minus AX must be 0. Now multiplying those in, A transpose A times X must equal A transpose times B. And now I want to take the inverse of A transpose A. And that only happens if this determinant is non-zero, and that in turn happens if the set of columns is a linearly independent set. Now that we need to prove. But just living with that for the moment, if I can take the inverse of A transpose A, then take the inverse of that and it leaves you with X. And then on the right hand side, A transpose A's inverse times A transpose. That multiplied by B gives you X. And that matrix there, A transpose A inverse times A transpose, is called the pseudo inverse of the matrix A. So we can get X by taking the pseudo inverse of A times B. And usually that's denoted by a little A plus. So A plus is A transpose A's inverse times A transpose. And what we've established then is that the vector X obtained by the pseudo inverse times B is that vector, so that the norm of the vector AX minus B, the length of the vector, is a minimum. And MATLAB has got a very convenient operator, this backslash operator. If AX equals B, then you can get X by taking A backslash B. As if, just think of it, you're dividing by A on both sides. You're not really doing that, but that's the way you're thinking of it. AX equals B, then A backslash B gives you X. So that's a MATLAB operator, A backslash B. It just means pseudo inverse of A times B. Let's just try it out, just to illustrate it. Here's a matrix A and the corresponding B. Take the pseudo inverse of this and take what we said was the pseudo inverse, A transpose A's inverse times A transpose. It's the same thing. So there you are. Now this is what we wanted to minimize. We've got MA being this, remember M was this list of the X coordinates and a column of ones. Now there is MA. So to find A, we take the pseudo inverse of M times Y. And when you take M transpose M, this is what you get, and that should be ringing bells. We've seen that before in the previous investigation when we had the calculus approach. So I'm claiming that that is invertible. We solve M transpose M times X equals just M transpose times Y. There is the matrix M transpose M. Now you should take this matrix here to get a little piece of paper, write down the matrix M and write down the transpose and put them together and multiply them out and make sure you know you can see that this is what you get. Take this thing's transpose, so in other words, rows become columns, and multiply that by this one, m, and be sure that you can see that this is what you get. And that's exactly where we were with our previous investigation. Let's just set up a little example. We give ourselves a vector, just the numbers from 1 to 8. We make it into a column, and we get corresponding y values, and we perturb them by 10%. Then we make our matrix. So those are the x values, and this is our column of 1s. And we're trying to solve for MA equals y. And so we use the backslash operator, and that gives us A. This A is not such that MA actually equals y. It's such that MA minus y is as small as possible. So the norm of MA minus y is a minimum. So we can get it by the backslash operator, or that's exactly the same thing. This is pseudo-inverse. That's the MATLAB function pseudo-inverse. And we notice that MA is not exactly y, but MA is as close as possible to y. We need to now prove that pseudo-inverse does exist. And that depends on whether we can invert the matrix A transpose times A. Let's establish this theorem first. If you've got an M by N matrix, the rank of A transpose times A is the same as the rank of A. Now we can view A as a function. A is a matrix, and strictly speaking, associated with A is a transformation, a linear transformation. Associated with any matrix is a linear transformation. And of course, the matrix of this linear transformation is A. It's a function. A linear transformation is just a function with the special properties that its domain and the range are vector spaces, and it has the property of being linear. So here's a picture which describes a typical linear transformation TA associated with the matrix A. The kernel is the set of all vectors which map to zeros, and that is a subspace. And the range is the set of all values of AX as you range X through the whole of the domain. So it's the same concept as the range of a function from reals to reals. It's the collection of outputs when you apply that function to the whole domain. The range is a subspace, and its dimension is called the rank. So the rank of A is the dimension of this column space, this range of A. And for the kernel, we use the expression the nullity, which is the dimension of that subspace. And the fundamental theorem to do with these is that if you add up the dimension of the range and the dimension of the kernel, you get n. In other words, the rank plus the nullity is the whole of n. That's a fundamental theorem in linear algebra. So there's our picture again, and there's the nullity and the rank. And that matrix A transpose A is an n by n matrix. So then again, this applies, but to A transpose A. Now, we're going to show that the null space of A is the null space of A transpose A. Just in other words, if you take an element in the kernel of A, you must show that that element is in the kernel of A transpose A, and other way around. Any element in the kernel of A transpose A has got to be in the kernel of A. So one way around is obvious. If X is in the kernel, then AX is 0, and if you then apply A transpose to that, you again get 0, and that means X is in the kernel of A transpose A. Now, pause the video here. Get out a piece of paper and a pencil. and try and reverse this implication. Show that if X is in the kernel of A transpose A, then it's in the kernel of A. Now you need to do that. I'll give you a little hint. X is 0 if and only if its norm is 0, its length. Now pause it and see. Try and reverse this now. Show that if X is in the kernel of A transpose A, it's in the kernel of A. Right, have you done that? Right, here we go. If X is in the kernel of A transpose A, that means when you apply this matrix to X, you get 0. So if we take the transpose of X at the beginning, that's also 0. And remember how transposes works. The X transpose times A transpose is the transpose of AX. And here we've got a vector transpose times the vector. That's just the dot product. And the dot product of a vector with itself is the square of the length, and then that means that if the square of the length is 0, then the length or the norm is 0. And if that is the case, then AX equals 0. So there we have it. X is then in the kernel of A. So these are the same. The kernel of A is the same as the kernel of A transpose A. Now then, here we are. Since these are the same, then we'll get that then of course the nullity of A is the same as the nullity of A transpose A. Now we appeal to our fundamental theorem that the rank of A plus the nullity of A is equal to n. And the same thing applies to A transpose A. And now we've just shown that the nullity of A transpose A is the same as the nullity of A. So what do we get out of this? The rank of A transpose A is n minus the nullity, and that's equal to the rank of A, and hence the rank of A transpose A is the rank of A. So that means, finally, that if we've got an m by n matrix and we look at the set of columns, we can now show that if this set of columns is linearly independent, then the inverse exists. Now, if the inverse exists, it means that the rank of A is the whole of n. You can't have a function is invertible if and only if it's 1 to 1. So if the kernel is not trivial, if the nullity of A is not 0, then it couldn't be 1 to 1. So having an inverse means that the kernel must be just the set with 0 in it. That's all. And that means its nullity is 0. So that exists if and only if it's got full rank. The rank of A transpose A is the dimension of the whole space, which is n. In other words, the rank of A is equal to n. And that happens if and only if that set of columns is linearly independent. We've looked at linear regression, which is the very simple process of fitting a straight line to the data points. If we've got one-dimensional input and one-dimensional output, we can then use our knowledge and our experience of functions to propose a regression function. So, for example, this looks like it's decaying up to a level. So it might be a function of the type m times 1 minus e to the minus kx. That diminishes to 0, and so f of x approaches m as x increases. And here we've got two parameters, m and k. So if we wanted to fit that function to this data using our calculus method, we take the sum of the squares of the errors, and now we take dsdm equal to 0 and dsdk equal to 0. Now that's going to give you two non-linear equations. So this is very much different from the case when we just had fitting a linear function. We ended up with a system of linear equations. Now we end up with a system of non-linear equations, and you need to, in almost all cases, use numerical methods to solve. If we're fitting curves to data, we need to be able to assess how well we are doing. So let's take this as a kind of a template. We've got data points xi, yi, and those are flagged by this little use an open circle to mark it. That's a marker for it. And this is the value of our fitting function f at xi. And let's make then, just for notational ease, we'll call zi the value of the function at xi. And we make these three vectors. So vector x, all these x points, vector y, all these y points, and z is the value, is the vector with all the values of the function in it. And the error will be y minus z. It's a vector. At each point here, at each xi, we form this error vector, the difference between the y value and the z value, which is the fitting function's value. That's an error vector. And we want the sum of the squares of the errors to be 0. We call this, if this is a vector E, we call the variance the average of the sum of the squares of the errors. So in other words, you take the sum of the squares of the errors and divide by n. The average of those is called the variance, or the mean square error. And the square root of that is called the standard deviation. And now I know that the statisticians prefer to divide by n minus 1 here. But let's, of course, for n being relatively large, it's not going to make much difference. We just need a simple number which is going to give us an assessment. So we're going to take this as our definition of variance. The sum of the squares of the errors divided by the number in it. Now, this is the average of the sum of the squares of the errors. Just to see how that works, we'll make a simple example again with our perturb function. And now we'll set it up as we had before. And there's our vector A. And we then make a polynomial whose values are the values of the linear function with the coefficients in A1 and A0. And then we get the error. And then if we want the variance, we take the sum of the squares of the errors divided by the number in it. In other words, the average of the sum of the squares of the errors. That's the variance, and the square root of that is the standard deviation. The covariance we define like so, and it gives us a measure of how the changes in one variable are associated in some way with the changes in the other variable, the covariance. Now, MATLAB has a function which will compute that for you, and it's represented in a matrix. So there is the covariance of y versus z represented in a matrix. And if we want to normalize that, we'll divide by the corresponding standard deviations. And so that gives us what we call the correlation coefficient. And there it is. That's a measure of the correlation between the two variables, between 1 and 2 and 2 and 1. And we can pick out the one we want, 1, 2. And if we then do a translation, so here this is the y bar is the average of all the y's. If we replace y minus y bar with all just by y and make a new vector, so we are going to translate so that the average is at 0. So we replace our new values of y are going to be y minus the average. New values of z, z minus the average. Then this becomes just y and z here squared each. And those then, that's the norm of the y vector, because we've got the square root here, and the norm of the z vector. And that might ring a bell. With our cosine formula, that's just the cosine of the angle between the vectors y and z. So we get a picture. If this is the vector y and the vector z, this covariance is the cosine of the angle between them. If that theta was 0, cosine of the angle would be 1, and they are both moving in the same direction. So they're strongly correlated. And the bigger this angle gets, as it gets towards pi over 2, the smaller the degree of correlation. And the one which we will use quite a lot is this coefficient of determination, R squared statistic. And it compares how well our fitting function does to the simple fitting function, which is just the average of all the values. So if we take the average of all of the y's here, that fits the data. If the curve is like this, it's not fitting it very well. So we're going to look at, we're going to take 1 minus round the sum of the squares of the errors between the y values and our fitting function, the z function here. And then we'll divide by the sum of the squares of the errors between the y values and just the average. So we're taking that y bar there as a fitting function, as a reference one. And so you can see that if the values of z are spot on to the y, so it fits exactly, then this will become 0, and the r squared coefficient will be 1. That's the first prize. That's as good as it can get. And that's a perfect fit. If this were 0, then if r squared were equal to 0, that means this is equal to 1. That means the values of our fitting function are doing the same sort of thing as the values of just putting in y bar. Our fitting function is not fitting any better than by just taking the average, so that's a poor fit. And we will be looking for a measure of how well our functions fit. So we'll use this R squared statistic we will use that as a measure. So we want our R squared to be up near 1 for our function to be fitting well. Of course, if it's less than 0, it's no good at all. Just to have a look at that, we set this up. We say y equal to cosine x, and we perturb the values a bit, and we polyfit it. In other words, we find the coefficient of a polynomial that fits it. We then evaluate it. Polyval evaluates that polynomial with these coefficients in a at x. And then we have a look at them. There's y and there's z. So y are the values that we're trying to fit, and z are the values of the fitting polynomial. And if we plot them, then they look like so. And what is the R squared statistic? The coefficient of determination. We compute that here. R2 is 0.977. All right, I've been blathering away for quite a while. It is now time for you to do an exercise. I strongly believe that you learn mathematics by doing it. You don't learn that much by just listening to someone or watching something. You need to get out pencil and paper and do the mathematics. And also in this particular case, you need to get MATLAB up and running and solve these problems with the aid of MATLAB. I won't be talking too much while we go through this exercise, but you should pause this video now and try this exercise. Then have a go at this one. The whole point of this, we've been talking about regression, that a neural network is actually a generalized regression function. So these exercises on regression here they set the stage for what is coming. And then we used a lot of linear algebra, and we will be using this sort of process quite a bit. We will be looking at data, and we will be trying, that data will have arisen from some process, and we're going to try and simulate that process. Usually it's very, very complicated. And this idea here is pertaining to the fact that we can perhaps have a linear approximation to that process. So this is useful for what is going to follow. And similarly, the backslash and forward slash operators in MATLAB. You need to get used to those. And this is now just the output from that previous exercise. Have a look at how it well approximates. Now we're going to use MATLAB functions. I've made my own little homemade random number generator from the MATLAB one, RAND. And this is just my version. MATLAB's got its own, which is fine. Just the syntax here, it's making V is the output from this. It's going to be a matrix. And it's going to be a matrix of numbers which are between A and B. And the variable argument in here is the size of the object. So if it were 2 by 2, then we're just an ordinary matrix. If it's a 2 by 2 by 3, then it's a book with 3 pages, each of which contains 2 by 2 matrices, and so on. So this is my own homemade version. You should make your own, and also look up the documentation in the MATLAB help files. This is how it works. So here is a 2 by 5. It's making numbers between 2 and 5, and it's making 2 by 2 matrices. Here the output M. It's making numbers between -1 and 4. They're 2 by 3 matrices, each of them, and there are 2 pages of those. So there are 2 pages, page 1, page 2. On each page is a 2 by 3 matrix of random numbers, and the numbers are uniformly distributed between -1 and 4. So this makes integers. Explore this on your own. And there's a little exercise to get you used to the syntax here. Now look at the MATLAB version of that, and we'll need to be able to assess how well our neural networks are fitting the data. So I make a little function called R². I'll show you mine, but first you show me yours. So make a function which then performs that assessment, the coefficient of determination, the R² coefficient. Have a shot at this too. And here's some more exercises just to get you used to the pseudo-inverse of a matrix. So you should, at each of those exercises, you should pause the video and do them yourselves.